So we'll talk more about material relations. It's the continuation of the subject that we talked about last time. Last time we met, we talked a lot about what the actual curve of stress versus strain relationship might look like for a particular material. And if, say, we want to perform some exact analysis, we may want that accurate of a curve. But a lot of times the things that we're doing, we just want an approximate answer. And so especially if we're doing something by hand, we might approximate what the stress strain curve looks like. So we call this process or these approximations, we would call them material models. So it's a model for simplifying what the true behavior, let's be careful, let's not say true, the actual behavior looks like. So one of such model is elastic perfectly plastic. So if you're, yes, question.
You made a distinction between true and actual. Are we going to get into that, or that's
no? So I caught myself because when I use the word true, that indicates true stress and strain as opposed to engineering stress and strain. What I really meant to say was just the actual behavior of the material if you did a test. It could be true behavior or it could be engineering behavior, but I mean, what are you getting from a test as opposed to a simplification? So if we look at the elastic perfectly plastic behavior, that is a material that starts out linearly elastic. So we have a linear region here with a slope of E. That's our modulus of elasticity value. And then when we get to our yield stress, sigma capital Y, it performs in a manner that we call perfectly plastic, which means it elongates with no additional stress gain. So you have a horizontal plateau here. So that means once it reaches a point that it can carry a certain amount of stress, it just deforms somewhat continuously. There's no, you have what we call a plastic hinge. So that material is now moving freely due to that force, and there's no additional stress capacity. Okay. So if you were to load in, say, a displacement control, which means you're continuously putting more strain into this material, you first follow up this curve in the linear portion, and then you move across to the right. And at some point, at some strain value, so this is strain and this is stress, you might decide that you want to unload the specimen. Okay, so it's carrying a certain amount of load. We might want to unload it to zero load. Say we're done testing it. When you do that, the specimen is going to follow an unloading path that is parallel to the elastic loading path. So this slope here, that yellow is probably not the best choice of colors, but that slope there is E. Which means when we reach the point on the strain axis, we have zero stress. So we have zero load in this member, but yet we have a non-zero strain. That means that after we've completely unloaded this, where we take the specimen off the machine, it still has some amount of strain in it. So this portion that is underneath that unloading triangle is the recoverable strain. So it's recoverable. Excuse me. We call that the elastic strain. So the elastic strain is the portion of the strain that you will recover if you unload it. So it has a certain amount of extension. You take the load off, it's going to recoil a little bit. The remaining portion, this part that stays in the body, this is permanent. This is called plastic strain. Slightly interesting, it's permanent, but yet if you apply cyclic loading, so in particular, I'm thinking of bending. If you have a member that's, say, a cantilever, and you apply a load at the end and you bend it and you get it to go into its plastic region, and then you unload it, it's going to have a deformed shape. So it's going to end up kind of trailing down. But if you then take that over and you load it again and you push it into the plastic region going the other way, now it has a permanent deformation the other way. And you can do this over and over again. Eventually your material will fatigue, but it's interesting, at least to me, that it's a permanent deformation, but by loading it the other way, you can change it to a different permanent deformation. But the point is that if you load it and then unload it, you're going to have some remaining strain in your member. Okay, now mathematically, in this situation, our elastic strain is mathematically the same as this strain that's under the initial elastic portion of the curve. So the elastic strain here is the same as the yield strain. Say we'll call this value our yield strain. But it's extremely important to me that you, despite the fact that in this model they have the same value, I want you to distinguish between the two. The yield strain is not the same thing as the elastic strain. The elastic region is the region prior to the yield strain, which means that if you're in that region, you're behaving elastically. Once your strain exceeds that yield strain, now you're behaving plastically. And numerically, they might end up being the same answer, but it's very different. The elastic strain is that last bit of strain that you're getting, that now you're getting back. The last bit of strain that you endured, but you get to recover. Does that make sense? So as you move along, your recoverable strain is always going to be this portion here that's under your unloading. Now that's important because these two are not going to be the same mathematically when we look at our next model. Excuse me. So in our second model, this is what we call a bilinear stress strain curve. So this is a bilinear material. Any guesses what it's going to look like? 2 lines, you got it. Technically, the other one was 2 lines as well, but one of them was flat. So this is 2 sloped lines. So we have an initial elastic section. So this has a slope of E. And now when we get to our yield stress, instead of flatlining, we're going to take on some secondary sloped line. And I'm going to call the slope of that alpha times E, because oftentimes we express that second slope as a percentage of our initial slope. And values of 2% to 5% are very common, in particular for steel, but kind of in that ballpark is a reasonable value. So now, if you were to load, you would initially start by moving up this elastic linear portion. You would then continue up the second slope. And at some point, you might say that you want to unload your specimen. So you would back off your loading. Oops. And that's going to follow a line that once again is parallel to your elastic loading line. But now, when you get down here and you measure your elastic strain, it's no longer equal to the yield strain. Because now, because our secondary slope was alpha times E, where alpha is non-zero, the stress at which we unloaded is larger than the yield stress, which means it creates a larger triangle, and then the base is larger. So now it's important that you understand the difference between the two. Any questions? Yeah.
On the first elastic perfectly plastic model on the snake, can the top line be any distance?
Yeah.
So you can kind of prove that they're the same, that the strains are the same by bringing the line all the way over to where it's almost non-existent and the triangles be over each other. That makes sense.
You can do that if you'd like. Yeah, yeah. Or you can look at similar triangles if they have the same height and the same slope on the hypotenuse, therefore they have to have the same base. And you can do that same logic on the bigger one if they have different heights but the same hypotenuse slope. Mathematically, you can prove that those bases are different. So in terms of how you might use these, your material testing will give you some curve that maybe looked like that. So if you were to choose elastic, perfectly plastic, you'd come in here and you'd fit this to your elastic region. And then you might fit this to your yielding region. And that point is your sigma y. And you'd call that your behavior. So as you can see, this type of a model fitting might be good if you don't expect your material to go very far into the plastic behavior. It might approximate the beginning of that curve quite well. But if you're really wanting to put your material into that full strain hardening, then this may start to diverge too much from your actual behavior. So you might choose the bilinear, in which case you'd probably end up with the same elastic region, but now you might fit that linear region to try to best fit your data. And in terms of the slope, depending on how much of the curve you're concerned about, your slope may vary. So if you're expecting a lower amount of strain, if you're expecting not to go beyond this point, well then maybe you flatten this slope out a little bit so that you're best fitting that first half of the curve. Whereas if you're wanting to take it all the way to fracture, maybe you do as I drew and you capture the best fit of all the data. Any questions before we move on? Yeah, Joe.
Do we consider thermal expansion and stuff like that when, I know this is totally not where we're at, but I know thermal expansion is going to change stress and strain.
We will talk about that today, actually. We'll talk about the effect of temperature on strain. Typically, when we're talking about our material behavior, it's not at a particular temperature, but it's at a temperature that's not changing. Okay. Usually within the lab, unless you force the temperature to change, it's not going to during the experiment. But we will talk about in the second kind of portion of the lab or the lecture about how we integrate changes in temperature into our calculations, because especially in mechanical engineering, you may be designing something that's going to be loaded and then experience significant temperature changes as your equipment cycles on and off and whatnot. Sure. Anything else? All right, so okay, but before we get to temperature, let's talk a little bit about strain energy. So strain energy is the energy that's stored in the body when an external load deforms the body. So we have a load acting on our object, it causes the body to deform, and that deformation results in some energy being stored. Excuse me. We refer to this as delta U. That is delta U is the symbol that we use to express strain energy. But perhaps an even more useful quantity than an absolute value of strain energy is the strain energy density. And we refer to that with a little u. That little u is the strain energy divided by the volume over which it occurs. Excuse me. So the energy that's absorbed divided by the volume in which it's absorbed gives us the strain energy density. So just like stress, we took a force and normalized it by an area. Here we're taking an energy and normalizing it by a volume to get more meaningful information out of this. And assuming linear elastic material, so assuming that we're in that linear elastic region, this ends up being 1/2 times the stress times the strain. More generally speaking, it's the area under the stress strain curve. But because of this linear relationship, that ends up being 1/2 the stress times the strain. And there's a little bit deeper explanation in your textbook, if you care to read it, that talks about deriving this equation. Excuse me. There are two very significant points on the stress strain curve where the area under the curve up till that point gives us some very meaningful information. Any guesses what those two important points are?
The upper yield and the UTS.
Upper yield is very close. Very close. What was the second one you said? The UTS? So UTS, not quite. But let's go with the first one. So the first one, he said the upper yield. More accurately, so let's say our yield stress. But the idea is that at the end of this elastic region, that's a very important point because that changes the way the material behaves. It behaves linear elastically up until this point, and then something different happens. And so if our intention is to keep this object behaving linear elastically, because we don't want any permanent deformations, then it's very important that we know how much energy can this object absorb before it deforms plastically. So we call that our modulus of resilience. And we signify it with UR. And so the area under the curve up until that point see if this is our curve. The area would be this triangular area here. Excuse me. And so we say that that's calculated by 1/2 the yield stress times the yield strain. And if you'd prefer to express it solely in terms of the yield stress and you don't want to have the other variable, you can do that because you know there's a linear relationship between stress and strain. So we can say this is 1/2 the yield stress quantity squared divided by E. Mathematically, it doesn't matter which way you say it, but sometimes you look up the value of yield stress and E quite easily. And in order to get the yield strain, you would have to calculate it from these other two values. So you might as well just plug them into this equation and save yourself one calculation. All right, so the UTS, the ultimate stress, was not the other point, but I said it was close. So what do you think the other key point is? Fracture, exactly. So in some cases, we don't want our material to deform plastically, and in probably all cases, we don't want our material to fracture. So if we look at our curve and we look at the area up till fracture, that's what we call the modulus of toughness. I don't have a quick and easy equation for you because it's going to depend entirely on the shape of the curve, which is no longer a constant. With linear elasticity, it's always a triangle, but this could be plastic or elastic perfectly plastic, it could be bilinear, or you might have an actual curve that you need to numerically evaluate the integral of that curve. So the area under a curve is the integral. And if you don't have a closed form equation, if it's just a bunch of data that was plotted from your experiment, what you need to do is get all of those data points, and each of those data points has some change in strain associated with them, and then you can calculate the area of each of these little rectangles, and you add them up. So if you can't integrate, you add up these little rectangles, which is fairly simple in MATLAB. MATLAB's a great, if you're doing experiments and post-processing data, I highly encourage you to get familiar with MATLAB, because in just a few short commands, you can take thousands of data points that maybe come from stress strain data and calculate this modulus of toughness. You can do it in Excel as well, but when you have thousands of data points, Excel gets a little bit clunky, and MATLAB, it's a breeze. Questions? Okay. So in structural engineering, excuse me, this idea of toughness is really important. And maybe in mechanical as well, but especially in structural engineering, because we have earthquakes. And an earthquake is the ground movement, but essentially that's a large amount of energy that's being put into a structure. And you want to make sure that your structure can absorb that energy without fracturing. And so that's, when we look at the types of materials that we use in construction, the amount of, the modulus of toughness is an important measure because it gives us information about how that material will absorb energy. All right, so I think I've mentioned the Poisson effect a few times in here, but today we are officially meeting it. We're going to formally cover that topic today. So the Poisson effect is the idea that if you have some type of material and you act on it with a force in a particular direction, we'll say this is the x direction. Excuse me. I think we're all in somewhat of agreement that it's going to extend. You all agree? Okay. But not only does it extend, the vast majority of materials will also contract in the perpendicular direction. There may be one or two that doesn't follow the rest of the rules of nature, but for the most part, if you extend in one direction, you contract in the other direction. And if you don't believe me, next time you're chewing gum, take it out of your mouth and pull on it and see what happens in the other direction, the orthogonal direction. So this ratio of the lateral strain, so I'll say the lateral strain, excuse me, is in the cross-sectional dimension, so the direction perpendicular to my load, divided by the longitudinal strain, longitudinal meaning the direction in which the load is applied, the ratio of those with a negative sign snuck in there is equal to what I call the Poisson, well, what everybody calls the Poisson ratio. Now, it's a personal irritant that there's a negative sign in here. I think its only purpose is so that we have positive values of Poisson ratios, which to me is unnecessary. We could have just taken the ratio of the orthogonal strain to the longitudinal strain, and that would turn out to be a negative number, and that would tell me that these are in different directions, and I'd be fine with that. But instead, it looks nice having a positive Poisson ratio when we tabulate it, and therefore we have to sneak a negative sign into the definition for appearances. And so, if we want to look at the calculation of strain, so if I want to look at the strain in the x direction, I know from before, excuse me, in previous classes, what this is. Can anybody remind me though? Yes, it's a change in length over initial length. How do I compute it given a stress value? Right, I'm going to divide my stress value by the modulus of elasticity. So if that is my strain in the longitudinal direction, and I want to express the strain in an orthogonal direction, which would be EY, I can do that using the Poisson ratio. So I know that the Poisson ratio times a negative longitudinal strain will give me a lateral strain. So I can say negative Poisson ratio times longitudinal strain, where longitudinal strain is sigma x over E. So I essentially took my strain in the x direction and multiplied it by a negative Poisson ratio. So once again, I'm irritated. Now I have a negative sign in this equation. I could have just not had a negative sign and had a negative Poisson ratio, and everything would have been one step simpler. But this is the Poisson ratio, not the Stillmaker ratio. So, you know, you get what you get. I didn't come up with it. Okay. So same thing in the z direction. This is another orthogonal direction that behaves the same as the y direction. Does everybody feel okay with this? Are you willing to accept it? It's good enough. Okay, excellent. So what if now I literally turn your world, not upside down, but 90 degrees rotated, and I say that instead of this being a sigma x, this was a sigma y. Now, how would I calculate the strains in these three directions? It's going to involve sigma y, yep. So they're all going to be functions of sigma y.
But now new is under
All right, so what Tolman is saying is that now my Poisson effect is occurring in the two directions that are orthogonal to y. Is that what you said?
Yeah.
So x and z. So I'd have X and Z would look like this. And the Y direction would be our typical stress strain relationship. All right, one more time. And now's your chance to show off. What happens if this is stress in the Z direction? How do I calculate those strains?
Poisson Effect is orthogonal to its directions.
All right. And we're going to use our Z stress. Okay. So is everyone okay with this? It's the same exact phenomenon. I'm just looking at it in 3 different directions. Which you might be saying, like, why are you making us go through this? This is painstakingly obvious, perhaps. Well, one, either it wasn't, and then I'm glad I went through it, or it was, but I wanted to go through it to lead you to this next step. And this next step, I want you to think about what happens if I have all 3 of these stresses. What happens if I have a small cube of material that has a sigma X, sigma Y, and a sigma Z? What do you think happens then? Patrick.
So for like the strain of the X would be just add up strain of the X or the stress in the X plus the strain in the X plus stress in the Y.
Exactly. What Patrick is saying is that if you want to know the strain in a particular direction, say the X direction, you would add up the strains caused by each of the 3 stresses. So sigma X, sigma Y, and sigma Z each caused a strain in the X direction. If we add or superimpose those, so add them together, we'll find the net strain in that direction. That's absolutely correct. So if we have a 3D stress state, which is what I just described, we have stresses in the 3 different directions. Then the equations for our strain become 1 over E times the stress in that direction minus the Poisson ratio times the sum of the other 2 stresses. Let's not forget the E there. Everything needs an E. Okay, so you have the stress in the direction you're looking at divided by E minus Poisson over E times the sum of the other 2 stresses. So you can permeate that for the other combinations. Now this is sigma Y over E, and then we have the Poisson ratio with the sigma X and sigma Z terms. And we can do the same thing for Z. Now it's the sigma Z that's out in front, and the latter term has sigma X and sigma Y. And if we have plane stress, which means, for example, we only have 2 non-zero stress components, for example, it could be sigma X and sigma Y. These same 3 equations apply. These are general equations. In fact, this is called generalized Hooke's law. So it's really important that you remember that Hooke's law is actually what we're looking at here, where we have all 3 directions contributing to your strains. The simplification of stress equals strain times E, where you neglect the other 2 directions, is assuming a uniaxial stress. And so it only applies when you have 1 non-zero stress component. So it's really important that you remember that. But if one of your stress components is 0 and the other two normal stresses are non-zero, that would be a plane stress. You would plug in 0 for the one that is not non-zero, and you can simplify these equations. So for example, your strain in the x, in this case, would be 1 over E sigma x minus Poisson over E sigma y. Your strain in the y would be 1 over E sigma y minus Poisson sigma x. Now your strain in the z is negative Poisson over E times the sum of sigma x sigma y. So that strain in the E is going to be significantly smaller than the other two because there is no force acting in that direction. It's only being acted on by the Poisson effect. Any questions? All right, so if there aren't any questions, it's now time to talk about thermal effects. So if you heat an object or cool an object that causes a change in temperature, this change in temperature will cause strain to occur in your material. So how many of you have walked on a sidewalk? Concrete sidewalk. How many of you have observed that there are at regular intervals like a divot that goes across that sidewalk? What is that for?
Expansion.
It's for expansion of that concrete. So as the temperatures increase, the concrete's going to want to expand, and that gap gives it a place to do that. And more accurately, what it does is when cracking occurs due to expansion, or probably more likely due to contraction, it gives a weak plane where it guides that crack. That cross-section of the concrete is thinner there than anywhere else, so it tends to guide a crack to occur at that location, and then you don't see it because it's inside of that divot. It doesn't always work. You've also walked on sidewalks where you see cracks, and that's because they've tried to, they've heated up and then they've tried to cool, and that material is pulling away from each other, and that's where it let go. Okay, so temperature causes strains, but it does not cause stress unless something very specific happens. So if I have an object just sitting here, just sitting here, and I heat it up real hot, it's going to expand. But there won't be any stresses associated with that. In what situation will there be stresses associated with that?
What is inside of something?
Yes, when it's constricted. So if I have a rigid cylinder around it, stopping it from being able to expand, now it's going to develop stresses because the temperature makes it want to expand, but it's not allowed to. And so that restriction causes compressive stresses in there. I think compressive stresses. Then same thing happens if it's trying to contract, and perhaps it's attached to a rigid boundary, and so it can't contract. Now you're putting tensile stresses in it that are going to want to cause it to tear apart, tear away from the constraint. So unless deformation is restricted. When you have free expansion or contraction of a material, this will occur equally in each direction, provided that the material is isotropic. So provided it has the same coefficient of thermal expansion in all directions, which typically materials do, but I'm not going to guarantee it, but typical materials you'll be dealing with will. So as long as that's true, then you're going to see that it's going to want to expand the same in all directions. And because of that, because of the fact that it's expanding equally in all directions, there's no effect on your shear strain. So if you start out as a cube and you expand equally in each direction, you're still a cube. Even if you weren't a cube, and say you were a rectangle, you'll still be a rectangle at the end of the day. And so if though, however, one direction is prevented, well, no. One direction is prevented, the others will still, I don't know, I'd have to think about that more. Question?
You said like it doesn't cause stress unless like deformation restricted and it usually occurs in each direction. What if you have like a beam like fixed to a wall and it's contracting, so like there's a stress on the side that it's attached to but not on this side?
That will not cause stress because that one side will stay stationary, but the rest will contract towards it.
Okay.
If you attach it on both sides, now you have stress buildup. You have a question?
It was in regards to the kind of null effect on stress. What about like the bottom of my head is kind of like a bread dish. You have where it's constricted on all sides except for one, and it can essentially go that one direction.
Mm-hmm.
Is that similar to what he was just saying, where there's not going to be any stress on those states?
So let me clarify a couple things. There will be stress because it's wanting to expand in all three directions, but yet it's constricted in two. So there will be stresses. Now, to get more exact into your question, there near the attachment, there will probably be some stresses because technically speaking, that beam is also going to want to constrict in the cross-sectional dimension, and where it's fixed, it will not be able to do that. But when we get far away from that fixed point, there shouldn't be stresses. Okay. Did I get, and you're clear as I can. We'll come back to this topic when we cover axial forces. We'll have some problems with temperature. So, but in general, if it can expand freely, there won't be stresses. If you've got constraints, there will be some stresses involved. And depending on the types of constraints, I told you, so if it's constrained at both ends, now we're going to have stresses throughout. If it's just one end, we might have localized stresses, but overall the body is fairly without stress. All right, so as our temperature changes from some initial T0 value to a final value of T, it wants to have these strains in the three directions, and their magnitude will be equal to the coefficient of thermal expansion times the temperature change. And the reason for that is because this coefficient of thermal expansion is, by definition, the amount of strain that occurs when a temperature changes. Okay. And so if we want to calculate the change in volume per unit volume, that's the sum of the three stress components. I'm sorry, strain components. So if all we have is thermal expansion, and if each of those terms is alpha times the change in temperature, if we sum three of them, it's the same as taking 3 times alpha times the change in temperature. So I didn't leave a whole lot of room for it here, but I want to just show you that the application of force and the application of temperature change go together to cause strain. So for example, if you have a strain component that's calculated by 1 over E times sigma x minus the Poisson ratio over E times sigma y plus sigma z. You then add to it alpha T minus T naught. So those two superimpose, the effect of your stresses and the effect of your temperature change. And then you can rearrange these formulas to get stresses. So for example, if we're dealing with plane stress, we would get that E over 1 minus Poisson ratio squared times the quantity E strain X plus Poisson ratio strain Y minus E over 1 minus Poisson ratio alpha T minus T naught. So part of your homework is to go from the equations of strain as a function of stress to the equations for stress as a function of strain. I want you to go through that process to see that it's not that complex. It's just algebraic steps, and that way you feel comfortable using both of those equations and you know where they came from. And your homework is due Tuesday, remember, Tuesday night at 11:59. Okay. Any questions? All right.
Go back to, so is there a missing, like,
A squared
yeah,
on the Poisson? I don't believe so.
okay.
I had the same question. I'm kind of laughing because I had the same exact question in my other lecture. No, I don't believe it's missing. What I believe happens is in order to go from one set of equations to the other, they're functions of both the x variables and the y variables. So you have to kind of solve when you reverse one of the equations. So you have strain, say you have strain x, and you reverse it to be in terms of sigma x equals something. Now you still have your sigma y in there. Sigma z is 0 for plane stress, but you still have your sigma y in there. So then you kind of need to do the same thing with your sigma y and put it in terms of sigma x. But then you have two sigma x's, so you figure out how to get those out of, factored out together. And as a result, you end up with that 1 minus nu squared. Now, I don't believe you get that same thing over here because this term was never a part of a stress component term.
Okay.
So I think it's correct. If you care to go through the derivation, when the homework problem I asked you to do doesn't involve temperature. But if you care to go through this and prove that I'm wrong, I will give you some extra points.
Can you go back to the 3D stress and plane stress slide?
Yes.
So for the plane stress, the z direction,
Yes.
can you kind of break that down on how you went about that, just for that equation? Because I'm seeing
You're talking about this one here?
yeah, that one right there.
So I plugged in sigma z equals 0, and that gets rid of this term.
Mm-hmm.
And so that just leaves me with the second term.
Oh, okay. Perfect.
You're welcome. But I do think it's important to illustrate that when we talk about plane stress, that means that all of our stress components are in that one plane, but that does not mean that our strain components are all in that plane. I think that's a common mistake, that you think that everything has to be in that plane. There is something called plane strain, where we say that all of our strain components are in one direction, but that's very different and cannot really occur at the same time as plane stress. So the last slide I have, it says 12 slides. I think this is the last slide though. The last slide I have is on shear strain or shear behavior. So everything we've talked about up until now has been normal behavior, normal stress, normal strain. But you could do the same thing with shear behavior. Typically, when we talk about shear behavior, we're usually only talking about the elastic portion of the response. And so we might say that the elastic response is linear. And so that would mean that we have a curve like this, and there's some linear slope. But now, instead of labeling that E, we're going to give it the variable G. So G is our shear modulus. Also referred to as our modulus of rigidity. And there's a relationship between these different material properties. So G and E, so your modulus of rigidity, your modulus of elasticity, and your Poisson ratio are all constants for a given material, but they can't be 3 arbitrary numbers. There's a relationship that relates them together. And that relationship is G equals E over 2 times 1 plus the Poisson ratio. So when you're taking an exam or a quiz or something, you might feel like you weren't given the information you need because perhaps you need G and you weren't given G, but you might have been given your modulus of elasticity and your Poisson ratio, and you're expected to compute G with that information. So given any 2, you should be able to calculate the third. Another thing to note is that the Poisson effect only applies to normal behavior, not shear behavior. So that means that these shear components are independent of each other. So if we have tau xy, and that's equal to G times gamma xy, there is no interrelationship between the other stress and strain components. So each of them has a unique equation. And you can kind of think about that in terms of if you think about how something deforms. If you were to take a cube and you slide one plane past each other, the other directions don't slide. So this could really use a visual aid. But so if I have a cube and I slide it past each other, and say I had something that started out like so it starts out like this, and I slide the top and I keep the bottom steady, that thing will have rotated, but in this plane, it's still perpendicular. It's not changing its shape in that way. And so if I'm looking at something on this plane and I slide past, now I've done this, but in this direction, I've rotated it, but I haven't caused it to change angle. So they don't interrelate.